Welcome back to Calculus Universalis. Today we're going to be unlocking the most important theorem in all of calculus, the fundamental theorem of calculus, or as I like to call it, the bridge between derivatives and integrals. This is what makes everything in Unit 6 work. This is how we go from a graph of a rate to computing exact totals. Let's dive in and make this crystal clear. What is the fundamental theorem of calculus? If f is an antiderivative, here, if you have an integral from a to b of f of x dx, then you have this capital F minus capital F of a. This means you can evaluate a definite integral by finding the antiderivative of the function and subtracting. Accumulated change equals final amount minus initial amount. This is exactly what this represents. What you need to be able to do this, you must be able to find the antiderivative, plug it in the bounds, top minus bottom, and then this only works if the function is continuous. Let's go through three classic AP style examples. Evaluate an integral directly. 4/3. Step 2. We're going to plug in a bounds. So our first example is going to be the rate of water flowing into a tank. So our information provided is the rate of water flowing into a tank is given by RT 4T gal per minute. How much water flows in from t equals 2 to t equals 5? This is just the integral of the rate function. So if you have the integral of the rate function 4t dt, it's going to equal 4 times 2 to 5 t dt. Now when we take the antiderivative, we'll find our answer. What does a of x represent? A of x can represent the accumulated area under f of t from 0 to x. If f is positive, a is increasing. If f is negative, a is decreasing. So if you're matching graphs, a of x will reflect the next area from 0 to x. This helps you interpret accumulation graphs in the AP exam. So let's summarize what we learned today. Here's what you need to take away from FTC Part 1. It lets you evaluate definite integrals by finding antiderivatives. You can compute the formula that we learned. It tells you the total accumulated change over an interval. It works in real-world applications like water, distance, or growth. If f is the rate, then the integral is the amount. And you can practice by evaluating integrals, finding velocity and distance traveled, and the a of x equal your integrals. Next up in day 6, we're going to do FTC Part 2. What happens when you take the derivative of an integral if it's more useful than you think? And very testable. See you there.